Good afternoon. My name is Ludwig Fellstrom, and today Team 20 is presenting the Freshness First FPGA packet routing. Since I am the sole presenter, I'm going to be moving through this complete presentation, including the project description, users and background, intellectual property, ethics, concept selection, and conclusion. This is my overview. The project is about a specific problem in real-time systems, and that's that arrival order is not always the same as usefulness. If a newer packet replaces the meaning of an older one, a strict FIFO can make the consumer work through stale state before it reaches the current state. My proposal is a small FPGA demonstrator that makes that policy visible. It parses a defined packet format, compares the sequence number for the destination, keeps the newest valid update, and counts every packet it rejects. The point is not to claim that I built a commercial router. It's rather to prove the freshness policy in hardware with a bounded input stream and verify that policy. Next slide. Here is my project description. Here we see a controlled source sends bytes into the FPGA. The parser turns that byte stream into fields such as destination, type, sequence number, length, and maybe payload. And then the sequence number is the key field, because for each destination, the FPGA remembers the latest accepted sequence. When a new packet arrives, it doesn't blindly enter the FIFO. It is classified as accepted, duplicate, stale, or malformed. The design target is to make that destination decision within 850 megahertz clock cycles after the header is available. This makes the policy concrete and measurable. Moving on, for marketability, the audience isn't really someone shopping for a commercial router. The buyer is a student, maybe instructor or FPGA developer who wants a reliable learning package to work with. The Icebreaker and IcePi Zero campaigns show that people support FPGA products when the use case tools, examples, and setup path are clear. My campaign would not fund a new board. It would fund a validated lab package for hardware many classrooms already use. Using Monroe's sequence, attention, stale data, waste action, students need a reproducible packet lab, satisfaction, visualization, the user sees something accepted, and attention, that we approve the bounded baseline first. Moving on. Here's my problem statement, and it is deliberately narrow, I would say. The engineering challenge is not to build a production Ethernet router, It is to design and verify a compact FPGA packet processing demonstrator. The objectives are self-contained. Parse the packet, extract the fields, maintain one freshness state per destination, accept those newer packets, reject state and duplicate packets, expose counters, and finally pass simulation plus board tests. The most important constraint is also a strength. I'm not claiming a full Mac, IP, or TCP stack. This helps my project because it keeps it to something my evidence can prove. Moving on. The primary user is an electrical or computer engineering student. The design gives that user a complete path from packet bytes to hardware state. The second user is an instructor or reviewer who needs proof beyond a single demo. The third possible user I came up with is an FPGA developer exploring a small stateful design. The intended users are deliberately narrow. It's to demonstrate parsing, compare FIFO against latest value behavior, and practice verification with directed and randomized tests. The excluded users are just as important. They should not carry financial orders, safety alarms, private traffic, or anything that requires complete event history and verification. Moving on, for background. The two most useful references are Corundrum and DE0CV. Corundrum is much larger than this project, but it teaches the right design discipline. Packet movement, queue state, schedulers, and controlled paths should be separate. The DE0CV is the opposite scale. It has the FPGA, clocks, switches, LEDs, and 7-segment displays needed for a bounded classroom demo. The third project is NetFPGA Zoom. Here you see it. It is a serious research network card, but it is not the right baseline because it brings SFP plus ports, PCIe, and external memories. My project is to keep the same architectural thinking that these projects have while staying small enough that we can verify it. Moving on to my next slide. Why this project is better for stated use. This is where the product becomes persuasive, you know? The project is better for a stated use because it avoids solving the wrong problem. A high-speed NIC gives impressive hardware, but it adds PCIe, host drivers, DMA, and physical Ethernet. A new FPGA board creates a supply and support problem. A simple FIFO demo hides this point because the stale work still has to move through the queue. My proposal is better because the policy is explicit, and that is exactly what a course or workshop needs. Moving on, for intellectual property, the two most important patents are the GoTenna bind routing patent and the IBM external network coprocessor patent. Here we see both of them. The GoTenna patent is relevant because it uses packet fields and sequence information, but it does that inside a wireless mesh routing and rebroadcast method. My design avoids all this by using only one local FPGA table with no mesh, no neighbor reachability, and no rebroadcast. The IBM patent, on the other hand, is relevant because it involves a parser and packet processing hardware, but it is about connecting a network processor to an external coprocessor. It's more of a mesh. My design keeps the parser and comparator inside one FPGA. The third patent I reviewed is the financial information FPGA patent. This was developed by Google. The avoidance strategy there is simple. This project uses generic educational patents, not market feed messages or trading logic. So I think we're good on the intellectual property front. Exploring ethics now. The ethical issue is not that the FPGA is dangerous. You know, the issue is the loss policy. Imagine a monitoring system receives an alarm packet that a newer normal packet for the same normal packet for the same destination. A fractious first policy can show the newest state while hiding the fact that the alarm occurred. This solution is not to pretend this cannot happen. This solution is to make the policy explicit. The baseline expectation exposes rejected packets with counters and simulation logics, and the documentation says latest value modes are not appropriate for alarms, transactions, and other things. This is for where freshness matters. The stronger future vision is to keep this in mind. Moving on. Sorry, my camera keeps on turning off. The concept of the good life is in play here, you know? A freshness first router could imply that speed and present awareness are always better than memory and accountability. I reject that as a universal rule. The better concept is a transparent control. Freshness is a useful policy when the data represents replaceable state. It is not a moral upgrade over history. So design makes that loss visible, and it does that to its help by adding this transparency. Moving on to slide 12. The concept selection compared 4 architectures. A shared FIFO is a familiar but obsolete packet that still occupies memory and output time. Multiple per destination FIFOs are more flexible, but they can add a schedule and pointer behavior that would take time away from verifying that freshness rule. An external Ethernet front would make the demo look more like a networking equipment, but it would dominate the schedule and change the claim. The selected concept is one latest value slot per destination. This scores the highest because it directly expresses the need, keeps state small, and makes that verification tractable for a one-person project. This is my final concept here. It's the most important implementation rule. The most important implementation rule I have for my project is atomic commits. The parser does not write straight lines into a live destination slot. It stages that full packet first. And only after the packet passes validation does that comparator classify it. If the packet is newer, the sequence length, payload, and valid bit update as one logical transaction. If the packet is stale, duplicate, or malformed, the live state does not change and the appropriate counter increments. That rule is what makes this demo reliable and yet also renewable. This project is graded on evidence, so the verification plan matters. Directed tests hit the boundary cases, reset all destinations, duplicate stale packets, rollover values, and more. Randomized tests compare the hardware decision against a software model. Assertions check the local safety rules, especially that rejected packets cannot write live state. And after that, synthesis reports check timing and resources. Finally, the board demo represents a smaller known sequence so that the audience can see the same behavior on LEDs and the 7-segment displays. Finally, to review, the need is real because a rival order can force a system to act on stale updates. The product is a DE0CV FPGA demonstrator that keeps the newest valid packet for each destination. The proof is not just a visual demo. It is a defined packet format, an 8-cycle decision target, directed tests, randomized model checking, synthesis reports, and even a board sequence at the end. The ethical guardrail is that design exposes rejects and refuses claims for applications where every event must be preserved. We are ignoring history. The selected concept is latest value slots because it is the most direct, compact, and verifiable way to prove that policy. My recommendation here is to proceed with the bounded prototype, but I'll leave that up to you. Thank you.